Welcome. Today, we're exploring bituminous materials, the backbone of modern transportation infrastructure and structural waterproofing. Primarily derived from crude petroleum distillation, these hydrocarbon-rich substances encompass asphalt, bitumen, and mineral tars. What makes them indispensable across civil engineering is their unique viscoelastic behavior. They provide exceptional adhesive strength, total water impermeability, and the vital flexibility needed to endure heavy traffic loads and extreme temperature swings. From long-lasting highway pavements and airport runways to roofing membranes and foundation barriers, bituminous materials ensure durability across our built environment. Let's dive into their fundamental properties, classifications, and real-world applications. To understand how these materials perform, let's break down their core composition and physical nature. Bituminous materials are defined by the presence of bitumen, a black, highly viscous, and sticky hydrocarbon substance derived either from natural deposits or as a byproduct of crude petroleum distillation. Chemically, they are predominantly hydrocarbons, making up between 80 to 87%, with remaining fractions of nitrogen, sulfur, and oxygen. Physically, whether found naturally or manufactured, they exist as semi-solids or liquids. Crucially, they exhibit thermoplastic behavior, meaning they soften when heated and harden as they cool, making them exceptionally workable during construction. Next, let's look at the primary types of bituminous materials used in engineering. First is asphalt, our standard road paving mix, combining graded aggregates with 4 to 7% bitumen binder. To increase workability without high heat, we use cutback bitumen, thinned with volatile solvents that evaporate post-application, or bitumen emulsions, which suspend bitumen droplets in water for easy use in cold or wet conditions. We also have natural bitumen, like gilsonite, mined directly and blended into refined mixes to enhance performance. Finally, coal tar shares a similar look but is derived from coal distillation, though it is rarely used today due to environmental and health concerns. Now let's examine the essential engineering properties that dictate how bituminous materials perform in the field. First is viscosity, which must be balanced to ensure proper mixing and compaction during placement. Next, temperature susceptibility is critical. A good binder resists softening in high summer heat, while avoiding brittle cracking during winter freezes. The material must also maintain strong adhesion, binding tightly to aggregate surfaces to prevent water stripping. Finally, its long-term durability and natural waterproofing qualities ensure the structure resists mechanical wear, weathering, and moisture damage, ultimately protecting the foundation beneath. These properties make bituminous materials vital across several engineering applications. Their primary global role is in road construction, binding aggregate to produce tough asphalt concrete for highways and roadways. Beyond paving, their moisture-blocking capability is essential for waterproofing, serving in flat roofing systems, damp-proof courses, and underground foundations. They are also indispensable for ongoing repair and maintenance, from rapid pothole patching to protective surface dressing. Furthermore, their chemical resistance and binding strength make them ideal for heavy-duty infrastructure, like airport runways, bridge decks, water tanks, and dams. To ensure quality and suitability, bituminous mixtures and binders are classified and tested rigorously. On the classification side, we have paving-grade bitumen tailored for flexible pavements and industrial-grade bitumen designed for waterproofing membranes and specialized flooring. In construction, hot bituminous mixes are produced at high temperatures in asphalt plants, blending binders with graded aggregates to construct layered pavements. To verify these materials meet engineering standards, we perform a standard suite of laboratory tests, including penetration, softening point, ductility, viscosity, specific gravity, flash and fire points, and solubility and heat stability tests. Moving on from binders to architectural materials, let's explore the role of glass in modern engineering. Glass is a versatile construction material that balances structural demand, functional performance, and modern aesthetics. It brings in natural daylight while providing essential thermal and acoustic insulation and meeting strict occupant safety standards. By definition, glass is an inorganic, non-crystalline, amorphous solid. It is primarily made by fusing silica sand, soda, and lime, along with specific additives tailored for unique performance needs. Today, glass is manufactured in diverse forms and compositions to meet precise requirements for load-bearing strength, optical clarity, insulation, and impact resistance. Types of glass used in construction. Float glass, produced by floating molten glass on molten tin, resulting in clear, smooth sheets ideal for windows, facades, and doors. Sheet glass, manufactured through rolling processes, used for basic glazing, partitions, and shop fronts. Tempered, toughened glass, made by heat treatment to increase strength, shatters into dull-edged fragments for safety. Used for doors, curtain walls, and glass railing. Continuing with specialized glass types, laminated glass sandwiches and interlayer like PVB between glass panes, offering safety, UV resistance, and acoustic insulation for skylights and facades. Borosilicate glass, engineered with boron oxide, provides superior resistance against thermal and chemical shocks, making it standard in laboratories and specialized windows. For privacy and aesthetics, patterned or obscure glass provides textured diffusion in spaces like bathrooms. To improve energy efficiency, insulated glass units separate double or triple panes with air or gas gaps. Finally, various specialty glasses, such as wired, shatterproof, tinted, and low-E coatings, address specific functional demands. Understanding the functional properties of glass is key to selecting the right type for building design. First is transparency, providing natural daylighting and unobstructed views. In terms of strength and safety, engineered options like laminated and tempered glass resist high impacts and prevent dangerous shattering. For building physics, double and triple glazed units boost thermal performance, while specialized interlayers deliver high sound insulation against external noise. Finally, glass provides robust durability and chemical resistance, particularly in borosilicate variants, alongside extensive aesthetic versatility, offering diverse colors, patterns, and surface finishes for modern architectural expressions. These properties translate directly into major architectural and environmental advantages. Incorporating natural lighting enhances interior spaces while lowering daytime electricity demands. Modern glazing gives architects immense design flexibility without sacrificing functionality. With advanced insulated units, glass drives significant energy efficiency, regulating solar heat gain and providing exceptional thermal and acoustic comfort for occupants. Furthermore, high-performance variants deliver uncompromised safety and security. As a bonus to long-term sustainability, glass is highly recyclable and supports credits across modern green building rating systems. Despite its many benefits, working with glass presents several critical engineering challenges. Its inherent brittleness means improper manufacturing or installation can lead to sudden structural fracture. Specialized formulations, such as tempered or acoustic laminated glass, also come with significantly higher initial material costs. On-site handling and installation demand high precision and specialized labor, as even minor surface defects create severe stress points. Finally, differential thermal expansion poses a persistent risk. If installation tolerances fail to accommodate temperature shifts, thermal stresses can cause the glass to crack. Let's look at where glass is actively deployed in modern construction. First, standard windows and building facades rely on glass for natural daylighting, weatherproofing, and architectural aesthetics. Expanding on that, curtain walls utilize large, non-structural glass panels to enclose multi-story buildings, creating seamless visual connections between interior spaces and the outside world. Moving indoors, glass is widely specified for doors and interior partitions, offering durable space division while preserving an open, well-lit environment. Finally, skylights and overhead roof glazing channel natural sunlight directly into core building areas, reducing electrical lighting loads and maximizing overall energy performance. Beyond building envelopes, specialized structural and functional glass plays a critical role in interior and high-security engineering. For safety barriers, glass railings, balustrades, and staircases maintain fall protection while preserving sightlines and open aesthetics. When engineered with thick tempered or laminated panels, glass can even serve as structural flooring for walkways and observation decks. In acoustic control, multi-layered acoustic glass delivers effective soundproofing for recording studios, hospitals, and busy offices. Finally, in high-risk environments like banks and embassies, heavy-duty laminated glass provides critical safety and security, delivering certified resistance against forced entry, ballistic impacts, and blast pressures.